The second part was not view. Why I took this problem means I revisited. Considering an isolated generator of 500 MVA, the inertia constant M of that plant being 8 pu megawatt per pu on frequency on the machine base. The unit is supplying load of 400 MVA. The load changes by 1.5% for a 1% change in frequency. You can see here, load is 1.5% change with respect to 1% change in frequency. Draw the block diagram for the equivalent generator load system. So block diagram shall means a rectangle box with a transfer function inside. That's what transfer function is, the basic requirement here. Okay. Then for an increase of 10 megawatt in the load, determine the steady state frequency deviation and response. So we were doing in the earlier problem up to this point, whatever the problem we had seen here, up to this point, we are just obtaining the transfer function. Later, we have not seen how is that particular change in frequency deviation and response, that we have not seen. How it is being done in this problem, we will do. So once we have a value of M, value of D given with a common base of 1000, it is shifted. The content value, it's old base and new, what is the old base? See here. Why? One more thing I wanted to convey you. Why I took this problem? So this problem, 8 pu is the basis of 500. Then 8 into 500 become a real value, divided by 1000 become converting it to new value of 1000. So this I wanted to show you. In the earlier problem, I have shown you when you have certain pu basis, revised base, old base, kind of old calculation we have seen. In that perspective, just have taken. It is 8 pu. It is not in numerical data like a percentage or a fraction. So hence I took this. So value old base to the new base expected, converting this content into revised base of 1000. That is division has come here. So 1.5 into old base divided by the expected old base. When you multiply, it becomes a numerical value of that quantity. When I divide it by revised base, it is getting transformed into new base of your requirement. So this step I wanted to make you a note from the previous problem and this problem. There is a slight difference in approach here. Rest all is same. Once I get a M value, M is of 4, D value by numerical 1.5 into 4 divided by 1000, 0.6. So 1 by 2HS plus D. 1 divided by 2 into H. You can see here. 2H equal to M. 2H equal to 1M. So it is 4S plus D. So again, I have a block. Frequency deviation is the outcome of the transfer function of the generator plus load, electrical load, and mechanical input. This is being the simplification. Then you make this 1 plus STP. So make this constant 0.6 divider as well as take it to the numerator. So I'll be getting 1 plus STP. So S here, TPS 1 plus STP. TP is the time constant. S is the frequency response. It's multiplied over here. And the numerical in the numerator we get as a gain, KP. This become a power transfer gain, KP, TP 1 plus, like that. So this 1 by 2 HS plus D function, when I make it 1, definitely it took its shape as KPS by TPS plus 1, like this. So this is how a simple view can be done on this to get the transfer function of the plant. Then to determine the steady state frequency deviation and the response. This extensive work is there. We will not touch complete of because it is some other need. This problem is having some other graphical representation in the form of plot of a frequency and its deviation as a load change. This frequency response is there. We at least will study how is that frequency deviation is obtained from the next step. Then from this transfer function, let's move. It is the equivalent block diagram which was shown in the previous block, standard first order transfer function. The gain being the numerator 1.667 and the time constant in the denominator, which is TPS. So gain and time constant is mentioned here. Correct? Then there is a load increase of 10 MVA, which is mentioned here. Steady state frequency deviation is asked. For us, steady state frequency deviation is asked for a load increase of 10 MVA. Then for 10 MVA on the base of 1000 MVA, we are trying to convert per unit, 10 divided by 1000. The shipment in load is 0.01 pu with the mechanical power remaining the same. Therefore, frequency deviation is equal to the change in load into transfer function of the block. But what is this exactly? If you revisit the thing which I have just come to you today here, what is this? Yes, this block. Can you see this? Omega delta omega s equal to minus delta PL of s into transfer function of that. If I take this here, delta omega of s divided by this become a transfer function of this. That's why I visited this particular heading today once again. So I am in need of response of this system for the frequency deviation. Hence, what I'll be doing? This is known to me. Transfer function of the plant is known to me. When I operate it, I'll be able to get deviation, what is happening in the system. So very simple step ahead. Let me go back. Can you see here? Delta omega s equal to minus delta PL of s into transfer function of the plant. When I operate this, it is a step load change of 10 MVA, which is 0.01 pu. Therefore, it is 0.01 divided by s into 1 by 4s plus 0.6. So I put back the old one. I put back the old content here. This was referred for the simplicity here. Then when I want to solve this, to get back the deviation, take the inverse Laplace application. So it is in frequency domain. To get the time, I should get inverse Laplace transform applied. As you are known, it cannot be done that easily. Partial fractions technique should be utilized, or if you are good with approach of inverse Laplace, you can get this. So what is the answer for this? Become s square plus 0.15 s in the denominator. Then definitely numerator will be something a constant. Then it becomes the split term in partial fractions. Once I split it in the partial fractions manner, I can definitely get inverse Laplace transform of this by taking delta omega t equal to this become the constant into e raised to minus st. This particular s plus a, what you call as, it become exponential minus 0.15t minus this become the step function, only the constant comes in 0.01667. So what we got here is the steady state frequency response. That is the heading today I revisited. Steady state analysis of the particular ALFC of an area refers to this function where the step change what is noticed and the transfer function of the particular point, having it viewed transformed into a time domain, we can get what will be the response of that over a long time at a certain time of observation, like that. When I say steady state means the time elapsed is very infinite. Over a large period of time, what will be the change in frequency I would like to understand. Now, by substituting t equal to infinity in this, what I am going to get? You can see here, for a long time of t, steady state frequency deviation 0.01667 e power 0.15 t infinity. This turns to be a value totally z. This terms, first term goes 0. When I substitute t equal to infinity over here, then what remains is minus 0.01667. You can see delta omega t after a long time steady state achieved is only minus 0.01667. This is the steady state frequency deviation. The steady state frequency deviation is whatever the value minus 0.01667 pu. Then the steady state deviation is noticed. What is that frequency then? Actual frequency settled. So actual frequency settled can be if I have 1 pu as its base frequency. From the base frequency, this is a change noticed called as a deviation, delta f or delta omega. When I convert it to per unit, delta f and delta omega are one and the same because divided by delta, divided by f or divided by omega goes as 1. Therefore, at per unit value, delta f is same as delta omega. Therefore, if this is a deviation, then what is that new frequency then? New frequency is 1, which is the per unit basic, minus this value. When I do, it become 0.01667. 9833 pu. When I convert it to actual hertz, considering a system of 50 hertz, of course, it is not given here. 50 hertz is not mentioned here, I'm sure. Suppose if it is mentioned 50 hertz as a base, then what would be your answer? This per unit value of frequency, if I multiply it by 50, it will be 49.1665 hertz. This is a small dip in frequency. Notice whenever this system is experiencing a step change of 0.01 pu load here. Then this response, when I plot with respect to time, see that become a response plotted as a variation. Then this function is utilized. You can see here time and frequency deviation. This is a little extra work. Unless we have experimental simulation, we cannot do it that easily. But this graph shows the response is plotted as in the figure using this expression. You can see time in 0 time till 30, whatever the seconds scaling has been done, and frequency deviation, whatever has been noticed. It is exponentially declining over a large period of time, settles to 0 deviation. That's what the frequency deviation is noticed here. From this time constant and all, whatever the plot we can obtain, the time constant is 1 by 0.15, which is 6.67 seconds. We observe from the response the plot that the system reaches steady state is around 30 seconds. Approximately about 30 seconds later, system experienced a steady state frequency from being disturbed by a 0.01 pu load, able to come back to 50 hertz or a 1 pu over a period of 30 seconds. You can see that. So this is how approximately 5 time constant. It means this 30 second divided by 50 if you do, it is called cycles. So approximately 5 times cycle or 5 time constants, it's going to come back. So this is how a frequency response of a plant for a step change or a sudden load change can be understood. The problem which is trying to focus you is basically how to obtain a transfer function, how to find its steady state frequency deviation, how to represent the frequency response with respect to the deviation and time. By this expression, we can. This is the extension of the work what I wanted to project to you. Then this is a small work. This is what we have done already understood this. This is what additionally we got today, and this is additionally how a plot can be understood. Then similarly, in line with this, I have another problem, which I think we have seen this problem. So just a governor has an ALFC with a capacity of 2000, nominal load of 1500 megawatt, or inertia constant of 4.8, load damping nature of 1.2%, and base frequency of 50, and roof of that particular governor turbine in that area being 2.5 hertz per pu megawatt. Determine the primary ALFC parameters, nothing but transfer function relevant content you need to obtain. So that's what is KPS and TPS. So this problem, the first heading, determine the primary ALFC. For that, what you can see here, TS transfer function equal to 1 by 2HS plus T, or KP by 1 plus STP. Its transfer you can see KP by 1 plus STP at the end, which again require H, D like this. They have been given. H is given, D is given. Transforming them percentage to per unit, we have to work. That's been done. For D of 1.2 means load increase by 1.2% for every 1% change in frequency. Therefore, 1.2% change of load means what? What is the load right now? Normal load is 1500 megawatt. Capacity of generation is 2000 megawatt. And how to convert it into per unit then? Then 1500 into the 1.2%. If you multiply, that is how 1500 into 0.12, 12 divided by 100. When I multiply, I'll be getting 18 megawatt as a D change. 1% of frequency refers to 0.5 because of 50 hertz. Then I take a ratio. Change in load, change in frequency. This is 1.2% for every 1%. It becomes 18 divided by 0.5. When that D configured, D of 1.2 gets configured as 18 divided by 0.5, which become megawatt per hertz representation. This is called megawatt per hertz. When I divide it by capacity of the plant, which is 2000, it will become PU, per unit power in megawatt, per unit power per hertz. So this is the representation in D terms. D has to be in 0.018 PU megawatt per hertz for the transfer function to be obtained. Hence it becomes 1 by 2 HS plus D. Substitution of them, D, H being 4.8, you can say 2H multiplied plus D. So when I make this 1 plus ST function format, 0.018, when I take the denominator of this function and make it to numerator, it stands as 55.55 divided by 1 plus 533.33 S. For this, I'll be able to get the numerator is Kp, gain of the power system, hertz per megawatt, and this is being a time constant, which is 533.33 PUDs, because I have converted them into per unit. If I make it divided by 50, it become in seconds. It become in seconds, because cycles per second, when I multiply 50, it becomes seconds. So 10.66 is the time constant in seconds. This is how a simple problem, such problem you can expect in the exam. That's why if you view the old question papers, you will be able to get that. So therefore, you will be able to get very simple 2-line problem, but it requires a lot of thinking. You cannot simply do it unless you know the steps involved here. Therefore, little view is required on this. Once we get this, for an increase of 0.02 PU in the load, find the frequency drop without the governor control. See here, without the governor control. And the same thing with the governor control. And next is with the governor control, but frequency dependent loads are neglected. D we have to omit. Remove the D, work in as a repeat problem. This is something from the textbook. A case study is being done on the given power system plant for a variety of observations. For a simply a determination of transfer function, for a load change with a drop of frequency when governors are not there, and a load change with the governor action, load change without any frequency sensitive. Likewise, all the possible case studies have been put in this. This complete work cannot be the question for you. Only one case study or added second case, that's all. But for you, this is an opportunity to understand the relativeness of individual controls on a same plant, how the plant is going to reflect for the conditions. So let's take second one. Without governor control. When we know, when there is no governor control, frequency deviation is change in particular PL divided by D. Why only D? It is denominator 1 by R plus D. That is called as the total response from that plant. 1 by R. When there is no governor, droop is absent. 1 by R plus D. So that is totally absent. It becomes minus change in load divided by D. As we know, the load change is 0.02 PU pronounced. Therefore, the frequency deviation noticed in the problem without the governor is load change 0.02 divided by 0.018 as a D. When I work it out, see the value here. It is 1.11 hertz. Note that D is in megawatt per hertz. This is the decrement of frequency from the standard 1.11 hertz. Suppose this is a 50 hertz system. So 1.11 hertz is the drop noticed because there is no correction from the governor. That could be a drop only. When the governor is in action, let's see how the governor will correct this drop by the control actions then. It is called same equation, delta F equal to minus delta PL divided by this D now become 1 plus 1 by R along with that. Here governor action has come, R has come. So the same parameter 0.02 minus D of 0.018 plus 1 by 2.5 hertz per megawatt, whatever the value of is given. So R is utilized here. So when I utilize this, see the effect of change in frequency. A tremendous drop in frequency. You can see so much of deviation is noticed from the base 50. Now we see the drop or change here is very, very negligible because the droop is acting on that. Therefore, it is only 0.0478 hertz drop from base frequency. Hence, the governor control definitely makes the things superior. In this context, the case study next one says there is no frequency dependent loads. What will be the response of the particular area? You can see here in this when D is 0, when I made here droop 0, no governor action, this was the case study. When I make a D equal to 0, you can see here delta F is minus delta PL divided by 1 by R plus 0D. D is 0. So this would reflect minus 0.05 hertz, very close to the governor control. It means the frequency sensitive loads are very less sensitive in this area. Their impact is very negligible. So when the governor was there, governor with no frequency sensitive loads are not affecting that much. Hence, it is how this is visualized as the change in frequency from the base. Deviation noticed is very comparable with each other. Therefore, a word of caution, it means D and R units must be taken appropriately. Then we can just see a D value of 1.2%, some alternative work, how it can be done in alternative. This 1.1 hertz is reached. This is an alternative step mentioned, how it can be done. Again, 1.11 hertz in a different way of work it is being shown. So we'll not worry about this. If you can view it, anyhow, these videos and slides are there with you. You can get to these things. At least to know how this problem, see the depth of problem, so simple. 2 to 3 lines of presentation here, another 2 to 4 lines, causing you entire very complex problem simplified into very simple steps. But once you solve, understanding the case 1, case 2, case 3, then only you will be confident. So a small effort is required from your end. Okay, this is how this problem was put to you to take a condition of that. Next, moving to another similar problem, how this frequency deviation and other things are worked out. Look into this problem. Similar approach. The system consists of 4 identical generators feeding a total load of 250 megawatt. See here, some problems were putting you MVA, some problems were putting you MW kind of load. So I think you are getting mixed with the information. But don't worry, when I make them per unit, it gets dissolved. So divided by the base value makes the megawatt or MVA taken out of the picture. Therefore, we shall not worry. So therefore, only worry about the numerical values. When we convert by PU, it goes off of our difficulty. A 250 megawatt load is being fed by 4 identical generators of 100 MVA in a plant. The inertia of each machine is 5 on its own base. The load varies by 1.2% for every 1% change in frequency. I can say D is 1.2% in percent scale. If there is a drop of 10 megawatt of load, see the word drop. When there is a drop in load, what would be your effect? Frequency is superior than the base frequency. There could be a rise of frequency. This is how you must be very careful about the load or drop. Drop of load means frequency superior. Rejection of load means frequency superior. Additional load or additional stress on the plant means frequency diminishes. In this way, the keyword must be understood very properly. Otherwise, we may end into other pole. So 10 megawatt of load. Determine the speed deviation and plot it. So speed or frequency doesn't make a difference. So we need to be careful about this. Then let's see the choose the base of 100. It is not mentioned here. This textbook has taken always all the values of base of 100 and it is mentioned. If it is a question of examination, a base of 100 would be mentioned here. Base frequency of 50 would be mentioned here. Without fail, it must be a 1 line extra over here. Okay. Then let us work H. When all the 4 machines are working hand in hand. So each machine is having inertia constant of 5. Then net inertia constant of the total plant is total machines into inertia of each. I have picked this problem only for this reason. Earlier we had only 1 machine, H was given to us. Can you see here? H was given by whatever the 2H is M. Okay, it is like this given. Any problem if you go, H was given directly to us. Never said what it refers to. It refers to single machine. Now I have a problem which is making you a split thinking. There are 4 machines. Inertia constant of each is 5. Then total H of the unit plant become the number of plants generated into individual inertia. This is the grand value of H we should use in the numerical solution. This is my intention to show you when several generators are put in combination, H of each is given. What is that total H? So you will be having multiplication of that because of it, this will be identical will be given. So we have to calculate 5 into 4 as grand H. And load drop is mentioned. 10 megawatt drop. From what load? 250. Then you can see a load drop is 250 minus 10 as 240 actual load remaining. Then this 10 megawatt load is converted into per unit by taking the base of 100. This 0.1 pu. Then the value of D is given 1.2%. Then how to get it into representation on the base of on a value of 240. D for a load of 240. 240 is the load actual. 10 megawatt is rejected or removed. What is remaining? 240. On this 240, how is the play of D? D is on 240 like this way with the base of 100. It becomes 1.2 into 240 megawatt. 1.2 240 megawatt divided by 100 as a base conversion. This becomes 2.88. 2.88 is the D value after shifting it for actual load remaining on the plant as 240 and converting it to per unit as divided by 100. Then you are very sure, like 1 by 2 HS plus D concept. 1 divided by 2 HS. What is the H of the system? 20. 4 into 5 become total 20. 20 into 2, 2 HS. 2 HS means 40 plus the value of this constant. What is that? D. D becoming 2.88. Now when I convert this value, if I want, I can transfer. I can make it as KPS divided by 1 plus TPS. I can get gain of the plant. I can get the time constant of the plant. I can do in a differential manner. Or else, by next response is plot is there. When I want to plot, I should take inverse Laplace transform of the particular frequency deviation expression. Then I have to substitute the times and see how deviation is noticed. For that, my requirement is to obtain the omega S or the delta F of S in terms of transfer function product. Then it is shift of 0.1 pu load. Then I have minus 0.1 by S in minus 1 into transfer function of the plant. You can see the same steady state frequency response what I have shown you in the beginning of this session. The same thing, delta PL by S into TS transfer function of the plant equal to delta omega of S. Then using this function of products, I can take inverse Laplace transform using the partial fractions split. Then I can get it as 0.034721 when I take inside minus 0.034721 into e to the power minus 0.072t. It means when I shift it Kp by 1 plus STP, I'll be getting this transfer function at this revision. This is transformed. Then I can take this as A. A become minus 80 in the inverse lap. S plus A in the denominator become naturally e to the power minus 80 like this. So this is how this can be represented as a time domain representation of the particular deviation. Here I can plot for a very large time. If t being infinity, when I put an infinity here, this second term goes 0. What remains is 0.034721 into 1. That's all. That's the steady state deviation what I can get. Let's see being done here. The steady state deviation is 0.03472 pu because it is the first term. The first term, when I multiply with the 1, this remains. That's called after a long time, t equal to infinity, I can get the steady state deviation. So I can get this. This is also steady state frequency deviation. When I say speed, when it become a per unit, speed and frequency have no difference because of divide by 1500 or divide by 50. It has got it into a fraction of 1. Therefore, At PU representation, there is no discrimination of speed deviation or frequency deviation. Then steady state frequency now would be 1.03427 pu. Now please observe this. What is the meaning of 1.034? It is 0.0347 pu increment in the speed or frequency. It is because load rejection, load is dropped. When the load is dropped, frequency is superior. Then it is 1 plus 0.04. Can you see here? 1 is added to this. So this is not mentioned in the solution directly. 1 plus 0.03472 become 1.0347 superior state of frequency because of rejection of load. This is also equal to, if I multiply this frequency pu into 50, what I'll be getting? 51.736 hertz. So this is how the final state, steady state frequency of the combination of the generators 4 in number working for a 250 megawatt, suddenly a drop of 10 megawatt, superior frequency is noticed by the plant to 51.736 hertz. So when is that? We can check later. So therefore, the plot of deviation, plot with the time after having utilized this expression when t equal to 0, when t equal to 5, t equal to 10, in terms of time scale of seconds, I can obtain the omega, delta omega at certain time t. That can be plotted as the delta omega in terms of seconds, 5, 10, 15, 20, 30. Then the deviation is noticed respectively. A plot represents exponentially increasing. You can see exactly opposite response. This is exactly exponentially rising. Now you can see this problem which you have seen. It is declining in the earlier problem. Correct? Coming to steady state easily. This way, this is rising because of load rejection. There is a deviation increasing. In fact, we want to bring it to frequency deviation 0. But here load is suddenly removed by 10 megawatt. Then frequency has to be controlled to a steady state error equal to 0. This shows how is that dynamics of this load is experienced by the power system operation and control. So for all these, the best and the best controller, automatic load frequency controller, must be set appropriately to see to that such an observations are controlled well within the time duration specified. Therefore, it is how response is plotted by the representation of deviation and the time from the particular expression we obtain from the transfer function, steady and inverse Laplace function. This is how this problem give you still more insight how these problems are viewed systematically. The another problem, which is very simple, just I took it from Wood and Uhlenberg presentation from the great author of power system operation and control. The number of videos are available in YouTube from this great author. So his presentations are available on net, and some of the presentation I have chosen from his presentations to my presentation to you all. One problem I picked in this context is consider an isolated power system on a 1000 base. A base value of a system is 1000. There is a generator of 600 MVA whose inertia constant M is 7.6 pu megawatt per pu frequency on the machine base being 600. Total system base expected to be 1000 and a load of 400 MVA. The load changes by 2% for every 1% change in frequency. This is D. D becoming 2 here. So 2 on a percentage scale. So suppose the load increased by 10 MVA. See exactly opposite to calculation I am observing. The problem which just now I have seen, load decrease of 10 MVA I have seen. In this problem I am finding load increase by 10. Then what is the transient response of the system frequency? It means what will be the behavior of the system during that. Therefore, M is of 7.6 pu megawatt per pu frequency in second. To get it into pu, how to do it? 7.6 into its machine base divided by shifted base which I want. Convert this pu into a value of M first. Convert this pu to value. Take division by 1000, that will shift it to new base value pu. This is how M is converted to 4.56 pu on the base of 1000. Similarly, D is in percentage. D is of what? 2% for every 1% change in frequency. Then it is 2 into, what is the load value? 400. 2% of 400 is a change divided by the value of base of the system. Convert it to D into PU. D became 0.80 PU. Now I got M in PU, D in PU. I am in a very quite sure state to represent the transfer function of the plant and its response from the expression by taking inverse Laplace. Therefore, load change is 10 MVA. So it becomes 10 divided by 1000. It becomes 0.01. 0.01 divided by, it is a step change, step load. It becomes 0.01 divided by S. That transforms the frequency deviation delta omega S equal to 0.01 divided by S. You may ask me, why is there no minus here? There was a minus outside, this minus got cancelled, it become plus only. So it depends on how the author has presented. It should be minus actually. And there was a minus outside. As per the standard equation, both get cancelled out. Therefore, it is 0.01 divided by S into the transfer function of that 1 by 2hs plus d, 1 by 2hs plus d. This value comes out. Okay, so this how I think, where is the 2hs here? Hs plus d, not hs, m, because 2h equal to m here. It's given as a m. M is 2h, 0.56 nothing but 2h itself. So it is m directly, ms plus d. I go back, it is 1 by ms plus d. M equal to 2h in that regard. M is given to me and it is ms plus d directly. Okay, so now to get the steady state response of this deviation and the final frequency, what I should get? Take the inverse Laplace of this function. Then when I take inverse Laplace by taking it kp by 1 plus stp format, then make it a partial fraction and get as expression as delta omega t in time domain as 0.0125 exponential minus 0.175 t minus 0.0125. At steady state, when t is infinite, time is infinite, the first term goes 0. The first term goes 0. What the deviation stand here is minus 0.0125 pu. This is the steady state deviation that is not being worked out. Okay, so I will be conveying you, this is the final steady state deviation delta omega or delta f. If you want to get the final frequency, what you should do? If the base frequency is said to be 1 pu, which may be 50 or 60 base frequency, and this difference, that stand as the next version of the revised frequency. This is how you can understand this simple one page of workout, having understood the transfer function and its relation in terms of inverse Laplace to get time domain representation of that. Then if you want to plot it, response would be plotted. Then what is to be done? This response with this expression t equal to 0, what is the numerical content of this? T equal to 1 second, 2 second, 5 second. On that, you can plot a curve. Definitely curve looks this way. What is that problem which you have seen in the brief? This way, because it's a minus. Similar expression I have here, exponential minus the term. This kind of expression I have here. We will have a drop exponential to a steady state value. Similarly, this is going to represent you a dropping curve. So this way, this is to initiate. This I would have taken as the first problem. You would have lost the content. How it is going to become? What is the graph like that? Hence, I took you some other problems. Later, I am presenting this problem. This is actually the problem. Plot the frequency response if it is added here. The examples which we already studied should help you to extend this problem further. So these are the variety of problems which you will find in the textbook and other resources available. Then moving to the next, another important aspect, the transient response and dynamic responses. Before that, when the machine is operated in synchronism, naturally, when the load is rejected or a load is suddenly increased, the rotating machines get a momentum. The kinetic energy in the rotating machine keep dynamically adjusting, increase, decrease, like that. That definitely change the frequency of the system. How is that? The kinetic energy of the rotating machine or a mass reflect into the system control. In that perspective, we have two problems. The problem which is on your screen, and the problem which I wanted to show you here. These two are the very important problem have come in the exam. Really, they have come in the exam. This problem has really come, and this problem has really come in the examinations of VTU. If you can see old question papers of 10th scheme, it was 10EE82 in the earlier old scheme. It became 15 scheme. It became 17 scheme. It's going to become 18 scheme in the new course. But this variety of problem do remain the similar. So therefore, this problem has come number of times. But 8-mark work, can you see the work involved here? You can see the numbers here, that's all. And how it's being done, let's go ahead. A 100 MVA synchronous generator operates on full load at 50 Hertz. The load is reduced by 25 megawatt. Load is decreased. The steam valve begins to operate with a time lag of 0.5 seconds. Determine the change in frequency if inertia constant of the plant is 5. What do you understand from this? A 100 MVA synchronous generator operating on full load, delivering certain power. Let's say full load, because the full load is the keyword, 100 MVA. Suddenly, load is decreased by 25 megawatt. What would happen till the valves start closing the fuel to that to decrease the generation? Say some time is required for that. That is called lag timing of the steam valves to close. How long? They take 0.5 seconds. Once you give a command, close the valve, reduce the fuel to the turbine. That's what the command when the load is decreased. Otherwise, frequency become shooted up. In that perspective, valves have to be closed down. Then to command it and act on reality, really, the lag is 0.5 seconds. Till 0.5 seconds, this energy which 100 MVA which you are generating, you are delivering, reduced by 25 megawatt. Then 25 megawatt is floating extra. Till what second? 0.5 second. By the time valve closes, this 25 megawatt become 75 only. Means 25 is reduced, 100 becomes 75. Till 0.5 second, what the energy you are delivering is 100 MVA only. Then extra energy floating in the machines is 25 megawatt. Then where it will go? It is stored as a kinetic energy in the rotating machines. How that kinetic energy in the rotating machines, frequency of the system interconnected. That is the gist of this problem. Okay, so I would like to convey you how is that additional energy floating in the system till the valves close the valve for the fuel, the extra energy is converted into kinetic energy in the rotating machines. So that is what we want to connect, frequency and the energy in the system, how that cause change in the frequency. So let's go ahead how this is worked in a systematic manner. The stored kinetic energy in the machine, in any machine in the plant, is given as capacity of the machine and H constant of that. It means 100 MVA, 100 MVA into H of that 5 divided by 1000. Why it is given 1000? I will tell you. It is called GH. G is the capacity of the machine. H is the inertia constant of the plant or generator. When I operate, I have to write this kinetic energy stored in the form of kilowatt second. Then this to convert to kilowatt second divided by 1000. This is a standard mechanism of representation of stored energy in kilowatt second calculations. So GH divided by 1000 makes it kilowatt second. If the load is reduced by 25 megawatt, then the excess mechanical power before the steam valve start to operate. See, the same thing I was speaking. Before 0.5 second, steam valve do not reduce the valve of fuel for the turbine. It is able to reduce the valve or a position, change the position only at 0.5 second and later. Till that 0.5 second, there is an extra energy available. That's what is the meaning. If the load is reduced by 25 megawatt, then the excess mechanical power before the steam valve start operating is what you have reduced actually will exist till this point of time. That's what is 25 megawatt. the excess energy input in 0.5 second to the rotating machines or parts. At I'm going to calculate, because till 0.5 second walls are not going to change their wall positions. Then extra energy is there in the system, which is applied to the rotating machines. So that we call as excess energy accumulated in the rotating machine for the duration of 0.5 second till and later only, or till that extra energy must be taken into rotating machine by the rotating machine. That's called as energy input to all the rotating machine for the duration 0.5 second. Later only wall open is given as energy 25 megawatt. In terms of kilowatt, I should write 25 megawatt into 0.5 second divided by 1000. Why like this only? Divided by 1000. If I do this, become again kilowatt second. Hence I wrote directly 25 into 1000. I should write 25 into 10 to the power 6 into 0.5 divided by 1000. Divided by 1000, I did advance. 1000, 1000 I cancelled off. It become 25 kilowatt into 0.5. 1000 I cancelled. It became 0.125 into 10 to the power kilowatt second. Some take a fraction. Now, this is the total stored kinetic energy in the machine. This is the additional kinetic energy getting supplemented to the rotating machines for a duration of 0.5 second. Now I have a relationship. The kinetic energy is proportional to square of the frequency in the system. The kinetic energy is proportional to square of the frequency, or frequency is proportional to square root of the kinetic energy. This is the relationship exists in the rotating machines. Therefore, I write a relationship between these two, frequency and energy. I to combine. How is that? The frequency at the end of 0.5 second. So 0.5 second and till that 0.5 second, this is extra energy. Then later there is a nominal frequency I'm going to get. Means steady frequency I'm going to get. New frequency I'm going to get. That's called as the frequency at the end of 0.5 second after the operation of the valve is nominal frequency. What is that? Right now system is operating. Let's say 50 hertz given the problem, into ratio under the square root. What is that? Stored energy plus excess energy applied to the stored energy inside the square root. So this ratio I'm taking. Stored energy, which is 5 into 10 to the power 5 kilowatt second, plus excess energy 0.125 10 to the power 5 kilowatt second, divided by stored energy. Outside I have nominal frequency. This proportionality give me 50.62 hertz. Now you can see the nature is load drop is there. When there is a drop of load, what is your experience? Frequency must shoot up. That's what I'm getting. 50 was the nominal frequency when it was delivering full load. Suddenly 25 megawatt is reduced. Then frequency must shoot above 50 hertz. What is that? You can see here. Nominal frequency it was working into square root of the energy differences. The energy stored revised 5 into 10 to the power 5. Original energy in the rotating machines, kinetic energy, plus accumulated energy for the duration of 0.5 lag, which is 0.125, total to the original energy in the rotating system under the square root. This ratio into base frequency stand as the revised frequency. There is no great work, just a rethinking is required. The load is reduced, this should superiorly increase. If the load is increased, suppose what would happen? This energy definitely reduce here. Stored energy minus this, definitely it will be lesser. Such problems we don't have in our observation. I have not seen a problem of that nature in the textbook. You can revisit yourself. So when it is load is increased, what will be the new frequency? You can just observe by placing minus over here and try to make this vision. It should be less than 50. So this is how this problem has come number of times in the word exam question paper. Kindly note, I made my own text to write here what I wanted to solve on board during the class days. Everything I wrote on the paper here. Then I put it as a PDF to you. So the relationship is kinetic energy and frequency square. Relationship is encashed. Very simple. Just in 5 minutes, 8 marks can be at your credit. This is how. Similarly, I have one more problem, little deviated from this. This is the one standard method of identification of change in frequency or a revised frequency in the system. Then we have another region, the same thing in a different manner. How is that? Kinetic energy ratios. Kinetic energy ratios, the same thing. Let me read it better. A 1000 MVA generator operate on full load at the rated frequency 50 Hz. Like my old problem, the load is reduced to 800 megawatt, correct? What is that down in shift down the load? 200 megawatt is the load down. The steam valve has an operating time lag of 0.6 seconds. So similarly, in my old problem, it was 0.5. H is 5 seconds. Determine the change in frequency. Is it a similar problem? Absolutely similar problem. You can just see additional knowledge you will get. This is the ratio which I am speaking. It means revised frequency is equal to base frequency F0 into root of revised kinetic energy to the base kinetic energy. Can you see this term? This term is what I have spoken here. Kinetic energy is proportional to frequency square, and I wrote this as the revised frequency is nominal frequency into root of revised energy to the old energy. The same thing is here. Revised kinetic energy to the base kinetic energy. How these two are connected? Like this. Kinetic energy initial is proportional to frequency square. Kinetic energy modified equal to base frequency new frequency square. So it is put in the expression. That's all. Which I was used is presented here. So this is a very similar problem later. GH, G into H. You can see it. 1000 MVA. 1000 MVA divided by 1000 is being done. It put as kilowatt second. So 1000 is already removed from this. 10 to the power 3 is done here directly. 1000 is eliminated divided by 1000 into 5. This becomes GH. That's called energy. The same thing what I did here. I did it divided by 1000. It is not being done. This author has presented directly. Kilowatt second means divided by 1000 is done. Then the load drop from 1000 to 800. That is decrement of 200. This is the additional energy floating till how many seconds? 0.6 seconds. Then this energy is accumulated into rotating machine. Then kinetic energy additional available in the system for 0.6 second is the shift down by load 200 megawatt divided by 1000 again. It is being done here. Divided by 1000 into lag kilowatt second. Same as my problem. 25 megawatt excess energy. Up to that 25 megawatt up to time kilowatt second. So these two are taken inside. This become 1.2 10 to the power 5. This became 5 10 to the power 6. So revised frequency is equal to nominal frequency into root of revised energy. Kinetic energy old, kinetic energy supplemented to the kinetic energy old under the root. This becomes revised frequency. So try to, this I think I have taken from K. Umarov text. So kindly note down. This is from VD question paper. This is from kinetic Umarov textbook. Such problem may be there in Nagar Kotari also. So kindly view how it is being solved systematically. So therefore, today we have seen 2 to 3 variety of problems which will definitely make your identity with respect to this module. Then transient response, a small paragraph which I have not shown you here. Just I have mentioned you how that response of a system matter you. This one slide of 2 to 3 lines are there, just a text. That's what we have to go through this. Then dynamic response, how the dynamic response of that particular transfer function and representation using simulation being worked out is presented in the book. It is not there, just a keyword for us. Later become how that automatic generation controller is now reviewed with only with the primary control of what we were discussing. Now the necessity of supplementary control has come into picture. That is what we have seen in the earlier class. Need for the proportional integral controller. Need for the proportional integral controller. This transfer function being like this way. A transfer function of the governor, transfer function of the mechanical turbine, and a transfer function of the area and load, electrical load, and droop. It was primary. It was primary only. Correct? When there is a need for the change to the dynamics of the particular load frequency dependent or sensitive loads, the necessity has come to make the response of this faster. Set point need to be changed. Then integral controller has come into picture. So this was necessitated a integral controller. We got it as supplementary control of ALFC. Then we visited this like this, a simple primary controller, which I have taken from some other text reference, a P reference, turbine, and governor and turbine, and a transfer function of the plant, and this is fed back to the error block, and it was a P reference, and it was working like this. Any load change, this error has to be gone back, and it has to adjust. And who will work for this? Who will set the speed reference point then? If the governor is not able to make out the error 0, deviation 0 here, then reference point shifting was necessitated. That was the need. Only the primary loop was uncontrolled case. You cannot control it because governor stalled at a certain limit only. Then how to reduce the error to 0? Then the necessity of revision of reference point was initiated. That's called a dotted line shows. This closing is expected. This data which you have frequency feedback, error feedback, has to be taken carefully. Error need to be amplified, integrated. Then that should become a reference point changer. This dotted line shows necessity is arised. Then that reference point is modified. Again, the primary loop become active in the situation. Therefore, this was visualized as need for the integral controller. Later, we call it as an ACE, error, area control error, etc. We will just see. In the previous class, just we took this concept, and here I added 2 more new diagrams for our clear understanding. The primary was only this much, and that necessitated us to think for speed reference point changing. Then a loop closing was done with the integral controller. Today we will see what is this meaning of this integral controller once again. You can see the purpose of integral controller is the for this purpose, whatever the error to be nullified and the dynamics of this particular response had to be improved, we need to set the reference point. Hence, integral controller is incorporated. The negative polarity indicates that there is a rise command. There is a minus command. You can see this is minus here. Minus gain divided by integral, which minus shows the negative sign indicates the error need to rise the command, open the valve or set the increased set point to the governor to operate more and more for the requirement. Later, the signal fed to the integrator is referred as ACE, area controller. In a magnified view, when I have a connected to single area, multi-area, ACE is the terminology we refer. Time being, integral controller get the feedback, and that will amplify, integrate the error and rise or fall the speed set point of the governor. Then P reference, what it does is minus gain of the integral block and integration of the error. So this is the function done by the particular integral controller. Taking the Laplace transform, what will get? P reference. So in frequency domain, Ki by S and delta F as S. This is from the feedback, integral controller, and P reference. This can be drawn as a transfer function. You can see when I want to represent this, delta omega S or delta F of S is available here, and that is multiplied with the integral to get the P reference. This plot give you P reference point on the act of deviation as an integral. Ki by S become integral of this error, and it will be set point change at the reference point. That's what is a reference. This is directly represented in the particular block diagram. And as long as error remains, then how long this will be active then? This integral controller will not be active all the time. This will be steady state, set a point, keep quiet. This keeps quiet. For this set point, this primary loop keep on working. Whenever primary loop fails to fulfill the control of delta F0, there comes a necessity of this Ki. It means this Ki always see this dotted line which is to be closed, error to be 0 here. If this is 0, this won't function anything. So this keep on working on the delta reference or change in set reference point till there exists a 0 error. That's the meaning which I mentioned here. As long as an error remains 0, and integrator output will increase. It keeps on increasing, causing the speed changer to move. When the frequency error has been reduced to zero, the integrator output ceases and speed changer position attains a constant value. It means this speed changer point, which is to be controlled, when the error becomes zero here, automatically this integrator controller will stop its function. This becomes a steady value which will be acting for the primary loop. That is the meaning of that. Integral controller will be in action as long as deviation is not zero. Once the deviation becomes zero, then automatically the output of the integral controller becomes static. That static value becomes the input to the particular requirement. So as long as it remains zero. So zero steady state frequency error following a step change. This is how this particular integral controller need has been necessitated. Still we have lot more to study from this in the next module. Therefore, it is our initiation. When the primary loop fails, the speed changer is inevitable. Integral controller to the control is inevitable. Hence, automatic load frequency controller necessitated addition of a supplementary control, theoretically and practically. Once it is necessary, how this performs, we have to go ahead in the next chapter itself. Meantime, I will see